Okay, Crewton Ramone's House of Math.com. More on division after cruising around the internet and finding some, how should we say, disturbing instances of people using base 10 blocks to try to show division, which of course is one of the least favorite topics of students everywhere, especially long division, and they get confused and everything. Okay, so the idea is to keep it easy and fun and to keep the patterns consistent, and this is why we do things. So this is a training for teachers, can also be used for teachers to teach other teachers, not so much as training for students, but of course if you're a student and you're watching, you can get some understanding also, but maybe not for the little kids because they might get bored. But the idea here is, why do we do what we do? Okay, why am I adamant about it? This is not just some good idea, just some fun thing that Jerry Mortensen came up with or something like that. The pattern is across and down for division. Now, people will say, well, that doesn't make sense because this side is 3 and this side is 5, and look, you told me that the rectangle is this is shorthand for rectangle. So why wouldn't I just put the 3 there and the 5? Because that's exactly what you see. Okay, I understand that. Well, because there's more math than this. Because we're going to do larger problems. Because we're going to wind up in algebra doing problems where you're going to need to mirror the notation exactly so that don't get confused when we're doing algebra and there's negative expressions and you're subtracting a negative and so forth. But let's keep it simple right here and just keep the pattern simple and easy to understand. Now, of course, 3 times 5 is 15, and then there's more problems because of the associative property. But here is the way you want to do it. And let me make that 3 nicer. All right. Now, wait a minute. It does no longer mirror. Okay, yes, it does, because what we're saying is if I have the whole thing is 15, it's 5 across and 3 down. It's 5 across and 3 down. We're going left to right. We're counting the across and the down. So now I just need to understand that when I draw my rectangle, when I make the symbols, I'm talking about it's 5 across. How far down is it? Okay. So if it's 5 across and the whole thing is 15, well then it's 3 down. Very simple. Okay? That's a hugely important understanding. People are like, why are you spending so much time on this? Because it's crucially important that you understand that the pattern for division is across and down. It's not optional. It's not, it's one of those things in math like 2 and 2 is 4. You get 2 and 2 is the same as 4, which is the same as 4 ones, which can be grouped again into 2 and 2. No, this is why I like mathematics, because you don't get to argue. You don't get, like, mathematics is a cold, hard mistress. She does not care. It's like, this is how it is. Alright, so using the blocks, I have 3 and 2. I'm going to do this. Make this one simple. I'll tell you what, I'll grab some 2s, even though it'd be easier just to grab some 3s, but holding the camera and doing everything at once, and I'm trying to be a one-take Eddie here and not stop and have to do editing. Alright, so here is simple problem here where I have, a very simple problem, where I have 156. And you can see this is just the same thing as these guys stuck together, right? So I mean, if you don't have the multiple 10s, it's no big deal. 3s and 2, right? Okay, but now they can really see, little kids can see that 3 and 2 is 5. And so forth. But anyway, okay. So I have here again 156. And people, well, why don't you just do this side is 12 and this side is 13? Well, we're going to run into some serious problems if we do that. Okay, but for mirroring the notation. And because now we just got a little bit bigger. We haven't gotten to the 4th degree. We haven't gotten to thousands. We're just fooling around with hundreds still. Take a look. If I do this, where you can see that this is that, and this is the well, now, when I show the notation, how am I going to show that? Well, what I would normally do, and let's talk about this algorithm for just a second that seems to be in many textbooks. Just saw another one, where the algorithm is explained like this. 12 goes into 15 once. So there's 12 into 15. and then we bring down, right? They don't even put the 0. There's just some algorithm that we're doing, and then we do some subtraction there, and then we know that that's a 6. Okay, and then 12, right? And then I messed up because I put the answer already because it was visually obvious here. But anyway, so I did the 1, 12 in there. Okay, and now I got to figure out how many 12s are in 36. Well, if I know my multiplication, that's an easy one because counting by 12s is super easy. Because it's just counting by 1s and then counting by 2s. But anyway, so 13 times is what you get. 3 times 12 gives me 36, and I'm done. How does that mirror what you see here? Take a second and just try and, right? And little kids will, 5-year-olds are the best because they'll just point that doesn't, what? Okay, so now I look at this, and instead we're going to do it with full understanding, and we're going to use the blocks, and we're going to do it the right way. But we're going to talk for a second about, again, people that try to say that it's okay to do it like this, and that we're keeping track. So then when I do this, they're going to walk up, right? Or they're going to walk across. When I take 1 times 12, I get 120. 120. Now that's good, because now at least we can see that it really is 10 times 12, and this is 120. It's not 12 in the 15, but really we have 156 as the total, and we're keeping track of subtraction with 10 times 12 being 120. Now, what's left? 36. But now look at it's sideways. Where's the line? This line right here is this line right here. Do you see that? Okay, so it's not so my notation does not mirror what I have going on here. But anyway, okay, I can still look over here and see that I have 36 left. Okay, so now I got to figure out how many 12s are in 36, and I can, as I'm walking across here, I can see that it's 3. 36. Now, what is the problem with just doing this? I mean, why are people even resistant to doing this, and why don't people understand how easy it makes it when you have this? Now I have 12 across, 13 down. Oh look, this line is this line. And I remember, I can tell you stories about us training teachers in Utah, and we left and we came back and they did split and shift, because you do split and shift with multiplication, and they did split and shift with division, I think was their reasoning. And we were like, what the, why would you, okay, anyway, then we corrected the problem, right? Because that's what you have to do. You have to have control of error, because you want your teachers to be creative, and you want your teachers to, you know, use Socratic method on themselves and go further. But you have to have everybody doing the same thing and explaining the mathematics in a way that everybody can get, and it's a uniform methodology, as we say. Okay, so we can see here now that that line and that line are the same. We can see that when I go 12 across, I go down 10, and I wind up with 120. Right? Because 10 times 12 is 120. And then I go down 3 more. Right? Oh wait, I didn't count what was left, because I get to here. Let's draw. Let's make a little thing where the guy gets to here, right? And he looks over here. Let's make it live. He looks over here, and he can see my drawing is 36 is left. So we've gone from here to here. Now we still have to go from here to here. We didn't count all the way, so you know, I just did this much, right? So now I can see that when I go to here, I'm not done yet. I have to go 3 more. Now little kids, all they're doing is counting. That's all they're doing. For the other kids, you're teaching them the algorithm that what you're going to do is keep track of subtraction. First, you start with the tens place. The most 12s I can get out of 156 is 120 12s. That's the most 12s I can get using tens. Okay, that's easy to understand. And then the most 12s I can get out of what's left, which is 36, right there, is 3. And in this problem, we have no remainder. Okay, so we made a perfect rectangle. So you teach them the algorithm and they understand what's going on. Now, how do you make division easy? Multiple ways to make division easy is, one, make sure that they know their multiplication, and make sure that they know how to subtract. Okay, now you can teach all of this all at once. Again, we don't have to know how to multiply and how to subtract as long as we have manipulatives and we can count. And now we can start learning while we do division about multiplication and subtraction. Now, in the standard form, or the standard method you'll see in most methodologies, is they want you to know multiplication and division, or excuse me, multiplication and subtraction before you know division. And Pshaw, I say. You use math to teach math. Okay, one other thing. Let's look at this again, where let's change the problem around, and we can now see that, look, I'm just going to change it, and I'm going to say, what if I put 13 over there instead of 12? Okay, because I'll see that, look, here is 13. And 12. And again, the problem is 13 is contained in 156 how many times? Okay, so I need to, oops, I'm being silly. There you go. Now here's the thing too, is when you're working with deaf kids, oh my goodness, I can tell you stories about working with deaf kids that just could not figure out what was going on when they didn't have the blocks and all they had was symbols. I was like, what are you doing to get this? More than one case. The first time it ever happened to me was in Nebraska. But more than one case where the kid just could not figure out what the heck you were trying to do. And I did the explanation, the mother did the sign, and then the mother burst into tears because her daughter signed back to her. That's all you wanted. And I mean, they had gone through all this huge rigmarole with special ed teachers and other teachers, and you know, calling the kid illiterate, and that, oh, this is just one concept that she's not able to get because she's deaf. No. And you know, the mom, anyway, it was such a relief for the mother to, and I seriously, this was like apparently months of problems, and I solved it in less than five minutes. Anyhow, and boy, did I have a reputation in the big O after that. Oklahoma. Anyhow, Oklahoma, no, Omaha, Nebraska. There you go. Depends on where you're from when they say big O. Now, we have this problem here where I have 13 is contained in 156 12 times, and if you try to show it like this, you run into the problem again. I've seen this where they actually do, where they put the 13 there, the 12 there, and the blocks are arranged like this. Now, first off, the pattern is across and down. But all right, let's be stubborn and try and explain it like this. So what you're going to have here, start off with nothing, is the whole thing is 156, one side's 13. So this is the side that's 13. All right, now, and I'll leave the blocks on top. How many 13s are contained in 15? That's the way they try to teach it. Well, let's talk about how many 13s are contained in 156. That's what we need to do. And we can see as I go over here, there's 10 of them. So I'm gonna, they just, you know, change the pattern and try to count from the bottom to the top. Okay, so I count 10, and then I have 130. And then this line and that line, right? We go there. Okay. And then how many 13s? Oh wait, what's left up there is 26. And then how many do I have? Well, I have, let's see here, I have 2 more to go across. And I have 26. Alright, here's the problem. Any little kid will look at this and want to start up here and go down. Why that is, I don't know. But I tell you, after 22 years in multiple classroom situations and hours and hours, I mean thousands of hours of tutoring, the kids will always want to start up here. So what they'll wind up doing, even if you show them once and they nod their heads and they're like, yep, okay, got it. What they'll wind up doing is they'll get the blocks out, they'll make the pattern, and then they can see that one side's 13, the other side has to be 12, and then they'll get confused about putting the 26, right? Because what are they doing? They're counting the 26. And then they come down here, and it's 130, and now, I mean, this is going to cause problems, I'm telling you, with alacrity. I'm telling you that this is going to cause problems. Alright, and then what do we got there? And then, okay. Well, how did you do that? Because I took 13, I put 2, and I put 26 there? Okay, I suppose you could, but that's not how we do it. That's not the way they're going to see it in any textbook. That's not the way it works, but that's not how they're going to do it. And it's going to become confusing later on when we do other problems. So what you want to do is just avoid the problem in the first place. Use a uniform methodology where everything stays the same. Consistently throughout all the division. When we get into the algebra, when we get into the higher power algebra, when we get into the negative numbers. Alright, but so here, again, 13. The whole thing is 156. This is called analysis, because we're spending just way too much time on this, but I have to bring home the point. What do I have? Alright, don't need to split and shift. Okay, we're just concentrating on division. We'll get into multiplication in just a second. Now I have 13 is contained in 156. How many times? Well, first I figure out how many times in that 10 is 130. Why? Because it's the first place. I can't get 100 out of there. There aren't hundreds, there's tens of them. This is a 10. Okay, and anywhere along here it's 10, actually. It's something you can bring home later. But alright, now I'm till here. There's my line. We're going down, right? There's a cross and down. This is how we read. We do not read, from the start to the bottom of the page and work our way up. It's uniform. It's consistent. Now I have 26 left. So now, how many 13s and 26? That's very easy to see. It's 2. I'm done. Now, how simple is that? Follows the pattern that you normally would have reading right to left down the page. Follows the pattern that will make it simple when we get into algebra and I have a problem where it's negative, where I have something like, say, x squared. Oh, let's just do it. Actually, I'm not going to do it because this is going to be a free video. I'll put negatives when we do negative algebra. But anyway, I'm going to tell you for sure. I have to get a password because there's videos that talk about it. When I have, say, something like negative, what am I going to do? Let's say negative 2x and negative 15, and I want to have one side be x minus 5. Okay, that's going to start getting tricky for students if they don't understand the across and down patterning. Now, this would be a good practice for you teachers, right? Because we're going to jump right up a level here, and you could pause the video and figure this out using the skills that you already have. And you'll see that really the across and down pattern will make this fairly easy to solve. Okay. Alright, so for those of you with a password, here is x squared minus 2x minus 15 shown using manipulatives. It really is, you can see, x minus 5 across. Now how far down is it? Well, if I go down, I can see that first I go down x, and I wind up with an x squared minus 5x. Uh-oh. Right? It's confusing, but it won't be, because now what's going to happen? Well, you have to remember that I'm going to take the opposite of this, right? Everything is the opposite, because I'm going to subtract now. So when I take the opposite, of course, x squared minus an x, right? But now when I take the opposite, right? We'll do this. Keep it easy. When I take the opposite, that's like adding, right? But really it is still the negative 5, but we are taking that away. So I wind up with, when I look down here, positive 3x. See them? Okay, and then what else? Minus 15. I'm just counting. Again, little kids can do this, right? Because all we're doing is counting. Okay, so let's keep our symbols correct, right? And I'm not going to use an arrow to go down, right? There's nothing there plus 0. I don't need, right? And I can see that really I don't need to put the 0 there. Okay, so now, have I got that? Alright, make sure it's all in frame. So now I have the minus 15 there, and I'm till here again. See how the nice pattern is uniform throughout? Okay, so what do I have to do? Well, I have to count over this, and I'm adding. I'm going more. I'm adding. I'm not taking away. I'm adding 3 more. Because when I do that, 3 times this gives me 3x, and 3 times that gives me negative 15. And then when I subtract, and see, this is where kids have a hard time. They get confused right there. I take the opposite. This is the same number. This was the same number. It was 3x minus 15. There it is, 3x minus 15. Now, it's the same number. when I take the opposite of it, a number that is itself, I get 0 every time. So you need to, right, and this is working out very nicely because it's all a nice perfect rectangle, but there's going to be times when it doesn't work out nicely. But they'll still be able to do it because they understand the pattern. They understand how and what they're doing. Okay, so, and they don't need the blocks, so you'll see they won't need the blocks. They're not going to be block dependent once they understand what's going on, they understand the concepts. So I subtract, and I wind up with nothing. That's it. See? Now, if you are doing a pattern that is different than this, I'm telling you, you're going to be in for trouble. Because they need to be able to see the across and down. And they need to have a uniform pattern that matches the methodology or the method that they've learned previous to this, and that you don't change it up when you get to algebra. You don't change. The pattern is consistent. It doesn't change when you're doing fractions. It doesn't change when you get to the calculus. It doesn't change when we get to higher power algebra, where this is x to the third or x to the fourth. It's still across and down. And this is the way you need to set it up, and so they can see it with the blocks or with the manipulatives. Okay. So thus endeth the password protected portion, and we're going to go back and do a quick thing about multiplication. But Crewton Ramone's houseofmath.com for more. Alright, so here we are at x squared, 5x, and 6. If I was in algebra, but as you can see, I'm not. I'm on the rough side, right? Because algebra is a smooth subject. Base 10 might be a little rougher because you have to add. But anyway, because you can combine terms. And tens can turn into hundreds, and units can turn into tens, but that never happens in algebra. Anyway, here is 12 across and 13 up. Okay, so 12 across, 13 up. Why do we do it this way? Again, so the blocks are not representing this part of it, but this part of it. Okay, so here, when we do our split and shift, we can see that these boxes are the same. That if I were to draw boxes around all of these guys, I have these boxes like this. And you're going to see where that 0 comes from. Okay, so, and there's no split and shift in division. So now I go across and up, and I'm looking at this portion, not this portion, when I want to count it. Okay, this is a key distinction for people to understand. So now it's very easy. Just count. If I'm a little kid, I don't need to know multiplication. All I need to know how to do is count. And we can go 6 in that box, because 3 times 2 is 6. But now it's 3 times 10 is 30. That's why this. Now, what's over here? Nothing. Nothing's there. In mathematics, we have a symbol for nothing. We call it 0. Big argument a couple of thousand years ago about why you need a symbol if it doesn't stand for anything. Anyway, okay, so then 10 times 2. That's why. 10 times, that's not 1 times 2. It's 10 times 2. And I get 20. There it is. Okay. Then, because I'll see that. Anyway, we'll skip over it. But the shortcomings of other things, like just do it the right so they understand. Now, what's 10 times 10? That's not 1 times 1. It's 10 times 10. 10 times 10 is 100. So what I have there is 120, or 120. Now I can add them together and get 156. Boy, that's the long way of doing things. But that's the way that gives them quite a bit of understanding. So now we can do cross multiplication. And people get confused with that term because they think of something else when we do cross multiplication. They're thinking, solving algebraic proportional problems. Anyway, so we could do it quickly and just look at it this way and say, look, 3 times 2 is 6, 3 tens and 2 tens is 5 tens, and 10 times 10 is 100, and we're done. Okay, so we skip that intermediate step. This is slightly more advanced, right? And so, like I said, you just continue to teach the same mathematics with more mathematics and get further and further. It's like when they first start counting on their fingers, and then they don't need their fingers anymore. And then when they're doing multiplication, it's great to count on your fingers, but it's better to get off your fingers and be able to have the problems in your head and know 3 times 2 is the same as 6. Because for little kids, little kids, when they first start with this problem, they have to count 1, 2, 3, 4, 5, 6, and it takes a long time. Now, when you get to bigger problems, it takes much longer because it takes a long time to count. But then if they start learning how to skip count and they understand the patterns, then they can just count 3, 6. Done. Very quickly. Right? Just 2 steps instead of 6 steps. Okay, so there is multiplication. And the point of this video was to bring it home that it's not just something neat or arbitrary across and down for division and across and up for multiplication. Okay, thus endeth this training for teachers and parents. Crewton Ramone's houseofmath.com for more.